from Miss Amanda. I am sub-teacher. They put me because I am math major, to be sub-teacher to Mr. Neil until
Okay.
to hiring the teacher.
Okay.
I'm confused what I have to give the student, like assignment or review or anything, like to keep them busy a little bit this week until to hiring the teacher.
Well, I don't teach those courses, so I don't know.
Geometry, actually, they were talking about geometry.
I know, but I don't teach geometry.
Okay.
So you'd need to ask one of the other geometry teachers. Let me see if I can send you. I'll have to look up a room number to tell you where to go.
There is a lady in the library, I think her name is Rebecca. She told me she has some material if I need that, so I'm not sure if the librarian.
Yeah, the rest of the geometry teachers will have a plan though, so they'll be able to tell you.
Okay.
7/1902. Okay, these two both teach geometry, so they'll be
Yes.
able to tell you where they're at and what
Yeah,
they
I
need to
know
be
the first one.
doing. Okay, you know Buchanan?
Yes.
He uses two different rooms, so I don't know which room he would be in right now.
Okay.
So I've listed both of them.
Okay.
But they would be able to tell you where they're at and probably give you a copy of something, of which worksheets to use. So,
Thank you.
uh-huh.
I guess it'll be 87.
I was on the Aqua field trip on Friday, so I wasn't here till like the second half of the unit. Do I have to take this test?
I can sign you up for prime time, but in the future, if you miss one for school business, that's considered a planned absence, and you need to be caught up by the time you get back. So I'll sign you up on Wednesday, and you'll need to watch the class recording to see what else you missed.
Mr. Townsend, I was also on that field trip.
Did you hear what I said to her?
Yes, yes.
Okay. All right, if you guys did not turn in the worksheet from last class 87, you need to either get that turned in the Google Classroom or bring me the hard copy. And I need you to put your phones and smartwatches up. So please do that during the minute of silence. And our quiz is no calculator, so please clear your desk
Today
out.
is Monday, February 26, 2024. Would you please join me in a minute of silence? Please stand if you are able and join me in the pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Thank you and have a great day.
Okay, I think the quiz is pretty straightforward on directions. Looks like it totals up to 20 points total, and it is pretty short, so we won't be spending that much time on it today, but you should still double check the work before you turn your quiz on. All right, is anybody still working? It's fine if you are. Okay. Guess that is it then. So let's go ahead and move on. So move on to the second section in this unit, which is 3.1. And again, just to be transparent with you guys, reviewing section 1.9 is really just us trying to help you out when we get the logarithms. It's not that we really feel like this is the most critical right now, but logarithms can be difficult for people. But again, we're still not quite to logarithms. We're going to spend, I think, 2 class periods on exponential functions. And then we'll move on to logarithms. Then we will have a 50-point test. And I think that probably wraps up around the spring break-ish time. We might get a little further than that. And then we'll do 2 more sections that also are logarithmic type stuff, and then do a second 50-point test. So that's where we're moving on to. All right, so you guys should have picked up 3 handouts today. 2 of them make up 89, the 3.1 notes. So just kind of remind you what an exponential function is, some of the characteristics, show you some of the applications we're going to do with that stuff, etc. And then 90 and 91 are on the same page. So the front is worksheet 1. So I'm going to do that one for you as examples. And then the back of that 91, you can see are the same question types. That's the one I'm going to ask you to do for practice after I go through one as an example. Now there is one question on worksheet 1 and 2 that we will wait to talk about next class, but otherwise we'll finish those up. All right, so you need to know what an exponential function is, and that is a function where your x or other variable is up in the exponent. So something like 2 to the x is considered an exponential function because x is up in the exponent. So for 2 to the x, if you did not know what the graph looks like, this is one where it's really in your interest to memorize a couple of these. But if you didn't know what it looks like, you should plug in some values. 2 to the 0 is 1, and that gives you a point. 2 to the first would be 2. 2 squared would be 4. And then if we do something like a half, 2 to the, to the negative 1. 2 to the negative 1 is the same thing as 1 over 2 to the positive 1. So that exponent rule we'll use quite a bit here. And you could, of course, plug in more points into a table, but this one grows exponentially. And the left side of the graph approaches 0. If you were to do the same thing with 3 to the x, again, just pretending like you didn't know what the graph looked like, maybe you plug in 0. 3 to the 0 would be 1, because anything to the 0 power is 1. If you don't remember that property, you're going to relearn it, because we're going to start using it about 10 times a class period for the next few weeks. 3 to the first could be 3. 3 squared could be 9. So we can see it also grows exponentially on the right side. And if I did something like negative 1, 3 to the negative 1 is the same thing as 1 over 3 to the positive 1. Anytime you have a negative exponent, you can just move it to the other side of a fraction and make it be a positive exponent. So same thing, you could plug in hundreds or thousands of points. That's basically what your calculator does, but this is what 3 to the x looks like. So what I want you to get out of these 2 examples is that 2 to the x and 3 to the x basically look the same. If we took the time out to do 5 to the x, 5 to the x would grow a little bit quicker. It would hug this x-axis a little bit quicker. Caitlin, you need to take your headphones off. Now's not the time to have those on. But otherwise, it's still basically going to look the same. 10 to the x is basically going to look the same. E to the x is basically going to look the same. Exponential growth functions, if there's no transformations, are all going to have a y-intercept of 1, hug the x-axis, and then grow like that. So how quickly they grow and how quickly they hug the x-axis change based on the number, but basically they all look the same. Okay, we could do the same idea with an exponential decay. So that is when this base is less than 1. So if we try to do a table here, you plug in 0, anything to the 0 power is 1. 1/2 to the 1 would be a half. 1/2 squared would be a fourth. Maybe go the other direction. 1/2 to the negative 1 is the same thing as 2 to the positive 1. So if you have a negative exponent on a fraction, you can change it to a positive exponent if you take the reciprocal. And same idea. More points, the better. I'll maybe do one more. 1/2 to the negative 2 is the same thing as 2 to the positive 2, or 4. And so essentially all that really happens is exponential decay looks like exponential growth, but it's been flipped over the y-axis. Now, I don't have this in our notes, but if we graphed 1/3 to the x, or 1/5 to the x, or 1/10 to the x, they're all basically going to look the same. They're all going to have the same y-intercept. They're all going to hug the x-axis on the right side, and they're all going to grow exponentially to the left side. How quickly they grow, how quickly they hug the x-axis just changes based on that base. But if you need specific, accurate points, you just plug in a few points like I did. But in general, if this base is bigger than 1, it's going to be exponential growth, so you should know the general shape of the graph. And if the base is less than 1, or between 0 and 1, because the negative would do something else, it's going to look like an exponential decay. These are the two that you want to kind of have a snapshot of in your head. Because we will do some transformations with those as well. So same transformation rules we've been using for years at this point. If you add to the parent function, it's going to go up that much. If you subtract from the parent function, it's going to go down that much. 6 and 7 are the two that are easy to switch up. If you add to x, it actually goes left, not right. When you subtract to x, it goes right that much. We talked about that with graphing trig functions last semester. That's not intuitive the way it is, but if you multiply the parent function by a negative, it flips it or reflects it over the x-axis. And the one you might want to put a star by, number 9, because you guys don't use this one as much. If you only multiply x, not the whole parent function, but just x, that's how you flip it over the y-axis. In fact, this one we just talked about with those two graphs up above. If 2 to the x looks like this, roughly, then 2 plugging in a negative x here, with exponent rules, this is the same thing as 1/2 to the positive x, which is really just a y-axis reflection. So, all right, so we will talk about graphing some of those. So we will graph the parent functions, shift them up, down, left, and right, maybe reflect them, and then answer some specific questions about them, like domain range, x and y intercept, when's it increasing, decreasing. So there's nothing for you to type up here, but these are just a couple of examples. If this basic function, here's some information about it. Here is an exponential decay example and some information about it. But you guys have seen that before, so you may not need to look at that one. Okay, on the front page, I threw out a couple of exponent rules just very quickly. And so when we're doing exponential functions, knowing our exponent rules is a little bit more important than on average. So I need to make sure that you know these, because we are going to live and die by these the next couple weeks. So let me go through and explain these 9 properties. Some of them are duplicates. And what you should do is circle the ones or put a star by the ones that seem less familiar to you. So starting over here, I've said this one a couple times already today. Anything to the 0 power is 1. So if you feel like you didn't remember that, you need to circle it and learn it as soon as possible. I've also talked about this one already today. If you have a negative exponent, you can move it to the other side of the fraction to make it be a positive exponent. Same thing with this one. An exponent of negative 3 in the denominator is the same thing as an exponent of positive 3 in the numerator. Just move it so that you have a positive exponent. And then even this one's the same too. X to the negative 4 in the numerator is the same thing as x to the positive 4 in the denominator. Always just move it to the other side of the fraction to give it a positive exponent. Over here, this one may look funny to you, but this one you're very familiar with. If I ask you what x times x is, I know you would all say x squared. And you're using this property. When you multiply things with the same base, you add the exponents. That's why it becomes a 2. Whereas if you want to divide things with the same exponents, you would subtract the exponents. So if it was something like this, you would probably think about it like 2 of these x's cancel out 2 of these x's and leave you 1x. But you can also think of it like this, where you subtract the exponents. You need to know how to take an exponent to an exponent. That's when you would multiply. So just a quick example, let's say x cubed squared. That would mean x cubed times x cubed, which would be x to the 6th. And you can see that in the end, we just really multiplied those exponents. If you take a whole fraction to an exponent, then each thing gets raised to that power. So this implies all of this is to the m, so not just the x, but also the y. And then an example with some numbers. 2x cubed would cube the 2 and the x, so it's actually 8x cubed. So again, each of you probably think some of those are harder than others, but please circle the ones that you know that you need to look back at before we keep on going. Okay, and then a couple applications that we look at. So we will do graphing exponentials, describing the graphs, and then there's 2 or 3 applications we look at. The most common one, and this shows up on the ACT, is compound interest formulas. So there are 2 of them, and we do expect you to memorize these 2. You should have seen these in Algebra 2 anyway. But some of these have a lot in common here. So depending on how many times you compound interest, depends on which formula you would use. If you compound continuously, you're going to use what's called the PERT formula. And if you compound instead a certain number of times per year, we would use this formula. I've heard students call this the print formula because it kind of looks like the word print mixed in there, but that's not a real official term. But when we use these, there's a lot of similarities here. Both of these have an A. This would be the amount that something's worth, or the amount that you owe. Both of these have a P, which stands for principal, or the starting amount. So that could go either way, either how much your loan starts out as, or how much your investment starts out as. But P represents your starting amount. T represents time in years. Both of these have a T. Both of these have an R. This would be the rate, and you need this as a decimal. So if your rate was 50%, you would do 0.50. If you put in 50 for R, that means 5,000%. It has to be typed in as a decimal. The 2 that are unique here is one of these formulas has an N and one of these formulas has an E. So E is a number. This is really just a number. In your calculator, you will access E by doing second divide. And at some point in your math career, especially if you're doing calculus next year, you need to know that E is about 2.718. It's kind of like pi in that it's irrational. It has a forever going decimal that doesn't repeat. And E stands for Euler, just as mathematician that came up with that number. So that only applies to the PERT formula. This formula doesn't have an E in it. This formula has a unique N in it. N is going to be the number of times compounded in a year. So if it was annually, that would mean N is 1. If you compound quarterly, N would be 4. If you compounded monthly, that means N would be 12. If it was daily, N would be 365. Just a few examples. So for those question types, you'll have to know the two formulas. You'll have to memorize them if you don't already have them memorized. You have to know what each of the parts mean, what to plug in for P, what to plug in for R and how to type it in, what to plug in for T, and then maybe plug in something for N, or maybe use E in your calculator, just depending on how often it compounds. I will tell you, actually on Friday in my calculus class, we actually had to use this formula for some calculus questions. So it does show back up in calculus. We will also talk about a half-life formula. So you're welcome to read through this if you'd like to, but I think once we see a few examples, you'll see what to do there. But half-life is a chemistry thing. A lot of stuff, radioactive material, medicine that you take, all kinds of stuff have half-life. And half-life means the amount of time it takes for half of that stuff to have decayed away. So we'll see a few examples there, but that's typed up for you as a good little resource. And we do not quiz you on this, but just so you know where this number comes from, Euler's number, that number that you need for the PERT formula, 2.71, I think it's about 2.719, I believe, 2.718. It comes from this. Just like pi comes from taking the circumference of any circle divided by its diameter, Euler's number comes from taking 1 plus 1 over x all to the x power as x gets bigger and bigger. So that's where it just naturally occurs. Okay, so all of that was just hopefully to jog some memories of some stuff about exponential functions, but now let's actually dive into what you will be held accountable for. So make sure you're on the right side here, worksheet 1. And I'm going to show you how I would approach these questions, and you can treat this first side as notes and just follow along with me, but of course please elaborate on your paper and give yourself some helpful hints as things come up. Alright, so the first thing is they're giving us a exponential function. This is an exponential function because the variable's up in the exponent. And they're asking us all kinds of questions about this thing. What's its domain, range, vertical, horizontal asymptotes? Is it increasing, decreasing? Is it concave up, concave down? What's its y-intercept? What's the point when x equals 1? Most of this stuff is pretty easy to answer if we know what this graph looks like. And this would be something we would ask you to do without a calculator. So when I look at all of this, and this is what I would suggest you do too. We're going to kind of do this in a few different steps up above. The parent function here is 3 to the x. So it's in your interest to know that an exponential growth has a y-intercept of 1, and it generally looks like this. That's accurate enough for now. This is what we did on the start of your notes page. Now, if I plug the number in for x, the first thing I would do is add 1 to it, which means my first transformation would be shift the graph left 1. So if I know what 3 to the x looks like, 3 to the x plus 1 is going to look the same, but it's going to be shifted left 1. So roughly like that. Okay, that stuff gives me the exponent on 3, and then the next thing I would do is multiply by a negative. So multiplying by a negative would look the same, except it's going to flip it over the x-axis. So roughly something like that. Doesn't have to be perfect. Just a rough sketch is going to be enough to answer most of this stuff. And then finally, the minus 1 on the outside is going to shift our graph down 1. So if I have a general idea of what it looks like before, I can estimate roughly down 1 from that. So this is what I'm going to be looking at to try to answer some of this stuff. All right, so first question, what is the domain? So sometimes it helps to look back at the previous steps as well. I know this goes slowly to the right here, but it does keep going to the right. So forever left, forever right. You shift it left 1, it's still going forever left, forever right. You flip it over the x-axis, it's still going forever left and forever right. You shift it down 1, it's still going forever left and forever right. The domain is negative infinity to positive infinity. The range is a little hard to see because this is a rough estimate, but this is where it helps to have these steps so you can kind of push yourself into it. This had a range of 0 to infinity. If I go left 1, that doesn't change the range. If I flip it over the x-axis, now it's negative infinity to 0, and then if I shift it down 1, it's negative infinity to negative 1. And it doesn't reach negative 1, so that would be a parentheses. So again, it's hard to see the range here, but you should know the range here. Understand left 1 doesn't do anything. Flipping it over the x-axis makes it the complete opposite, and then shifting it down 1 is how I'm keeping up with that. Okay, find the horizontal asymptote. So this one had a horizontal asymptote at y equals 0. Shift it left 1, it's still at y equals 0. Reflect it over the x-axis, it's still at y equals 0, but then I shifted it down 1. So now it is at y equals negative 1. That's a horizontal asymptote because it approaches it on the end of the graph but doesn't cross it. You might be tempted to say that it has a vertical asymptote because it kind of looks like it spikes here, but again, this domain, it just goes slowly to the right, but it does keep going to the right. So there is no vertical asymptote. Now, when we do logarithms next week, and logarithms are just the inverse of exponentials, and we're switching x and y, basically these two are going to switch. Logarithms will have a vertical asymptote, but not a horizontal asymptote. Okay, so reading this graph left to right, this graph is going down, which is what we would describe as decreasing. Just like you read a textbook left to right, you should read a graph left to right. It's going down over time. It is decreasing. This one's usually 50-50. Have y'all heard the terms concave up and concave down before? No? Okay. So concave up versus concave down is just how the graph opens up or opens down. Concave upward is like x squared, up like a cup, whereas concave downward opens down, down like a frown is the general saying. So when I look at these, the original one was concave up, it's opening upwards. Shift it left 1, it's still concave up, but then when I flip it over the x-axis, now it's concave down. Shift it down 1, it's still opening downward. So this is referred to as concave down or concave downward. And this idea of concavity ends up being a big topic in calculus. All right, what is the ordered pair when x equals 1? So I have my graph here, and I can estimate 1, I don't know, it's something negative. This is not accurate enough. I shouldn't just hope that I can guess this. We can do this algebraically. If I want to know what y is when x is 1, just plug 1x or plug 1 in for x into the equation and then solve. It's 1 negative 10. You don't have to guess based on your graph. H wants to know the y-intercept, and to me that's the same exact skill. Y-intercepts are when x is 0, so just plug in 0 for x and solve for y. Negative 4. Of course, you should make sure that it looks like your sketch. If you thought it was positive 4 and your sketch, the y-intercept definitely looks negative, then something's wrong. But just realize how these two are similar. Y-intercept, we're telling you x is 0, x is 1, we're telling you x is 1. Just plug them both into the equation and solve for y. Now, the next few are things that pretty much I've already thought about, so that's going to go pretty easy. State the 3 transformations in order. So I started off with the parent function. I thought about if I plugged the number in for x, the first thing I would do is add 1, which is how I knew the first transformation was left 1. The next change to the parent function was multiplying it by a negative, which reflects over x-axis. And then the last transformation was the minus 1 on the end, which shifted it down 1. So if you start off with the graph as I suggest, you really already thought about that and you just have to write that down. Okay, J is not a question we will quiz you on, but I still expect you to put it on here for your homework grade, but you're welcome to put an X next to it so you don't have to study it. Sometimes these are referred to as transcendental functions. That's not going to mean too much to you right now, but if you looked at a bunch of calculus books, a lot of calculus books say either late transcendental functions or early transcendental functions. And all that means is they deal with these type of functions early in the course or late in the course. Okay, H or K wants us to sketch this from above. So I did a real rough sketch to help me get all this information. But now that I have all this information, I can make a nice accurate sketch. So, for example, I know it goes to the point 0, negative 4 from part H. It goes through 1, negative 10 from part G. I know there's a horizontal asymptote at y equals negative 1. Remember, asymptotes you should graph as a dashed line. And from my sketch earlier, I know the general shape of the graph. So let's sketch it in. Same thing I had above, but now that I have a couple points and that exact horizontal asymptote, I can make it look more accurate. I would say on your quiz, I think we might ask you to specifically like make a table and plug in 3 or 5 points or something just to make sure it's accurate. All right, this asks if this is a one-to-one function. So we just talked about that. This does pass vertical and horizontal line test. These are the 2 tests it has to pass, and it does pass them. The number E that we're going to be using for some of these other questions is Euler's number. Again, I expect you to put this on your assignment for for the homework grade, but you can put an X to it where you don't have to study it. If you leave it blank, I'm not going to give you full credit because I'm doing this for you. But E comes from 1 plus 1 over x all to the x power as x approaches infinity. If you plug in a really big number in for x there, that's where the number E comes from, the 2.718. This is just a naturally occurring numerical pattern. Okay, this we're saving for next class. So don't worry about part A. And when I ask you to do worksheet B on the back, or worksheet 2 on the back, you can skip part A for this class period. You will have to have it done before you turn it in. But then the 2 application questions, so the compound interest and the half-life. So this question says we're going to invest this much money. So this is the starting amount, principal. We're going to earn this much interest, so that would be the rate, but that needs to be put in as a decimal. So I'm going to switch that before I forget. Over 30 years, which would be T. And then they're asking us to write the formula and the amount if we compounded this daily versus continuously. Well, continuously is probably going to be the easier one because this is PERT. So you plug in starting amount for P. E is a number, not a variable, so leave it E. Plug in the rate as a decimal, plug in the time, and assuming we make this no calculator as we've done in the past, we would let you just stop right here because you wouldn't have a calculator. But for us, I've got a calculator out already, so we might as well type it in and see that that's about $14,000. So you would be pretty hard pressed to get 6.5% interest anymore. But if you did have $2,000 you could set aside for 30 years and you could get that interest rate, then your $2,000 would be worth about $17,000 if you could leave it alone. Okay, now if your interest is compounded daily, that's going to be almost the same thing as continuously, but the formula is going to look a little different. So we're still going to put 2,000 in for P. We're still going to plug in R as a decimal. We're still going to plug in 30 for T. But this formula doesn't have an E in it, it has an N in it, where N represents the number of times it's compounded per year. So if it's compounded daily, N would be 365, and that goes in 2 places in the formula. So without a calculator, this is where you'd have to stop. But if we gave you a calculator, you could type that stuff in. It's about $14,054.93. So as I said, it's going to be almost the same as continuous. Continuous is always going to be a little bit higher, but if you're not touching your money for 30 years, you're probably not going to be concerned about $3 difference. So I assume you guys saw a lot of this in Algebra 2, or at least the formulas look familiar. Okay, good. Okay, you probably did not see this in Algebra 2, but these questions, these are not like you have to know any real chemistry or anything. I don't know any chemistry, but I can do these half-life type questions. So we skipped over this part in the notes, so make sure you pay a little bit closer attention here. So we've got a radioactive isotope that has a given amount of mass that follows this exponential equation, where T is measured in years. And one thing, these are the only 2 questions we had to ask you about these. What's its initial mass? So how much mass does it start off with? So that's going to be when t is 0. So you could say the amount of mass is equal to 40 times 1/2 to the 0 over 2007. And then you should be able to solve this without a calculator, because 0 divided by 2007 would be 0. Anything to the 0 power is 1. And 40 times 1 gives you 40. So the answer was actually sitting there in the equation, but you don't need to memorize that. Just plug in 0 for t and see how much mass there is at the start. Okay, and then for half-life, we're going to be interested in how many years have to pass before it reaches half of its initial mass. So if this formula tells us how much mass there is, and we know that he starts off with 40 grams, his half-life is going to be when he is deteriorated down to 20 grams. So again, you don't need to memorize any tricks to this question. Just set it equal to half of its initial mass, and then solve this equation. You could divide both sides by 40. Then you should notice the left side is 1/2 to the first, and the other side is 1/2 to the t over 2007. So for these two to be equal, we need to figure out when is t divided by 2007 equal to 1, and that would be when t is 2007. So after 2007 years, that 40 grams of radioactive isotope has gone down to 20 grams. And it would take another 2007 years to get down to 10 grams, and another 2007 years to get down to 5 grams. And I don't know if you've ever thought about this, but with medicine, all the medicine you guys take in your lifetime has a half-life. So anything you've ever taken in your lifetime, there's small trace amounts of it that are still in you and will always be in you, because it never reaches 0. It just gets smaller and smaller. Okay, so again, I know that's pretty quick here, but the idea is that hopefully you remember some of this from Algebra 2. But before I ask you to try Worksheet 2, which is the back, other than question A, you're welcome to skip that one. We'll worry about that next class. You've got enough information today to worry about that one. Is there anything from Worksheet 1 you would like to ask about or want me to describe again? Okay. Then the last thing I need from you guys today is I need you to try this Worksheet 2. Try to approach it just like we did Worksheet 1. Check your answers with my solutions online to make sure that you're doing it correctly. And then of course, anything that you have to flip the paper over to get a hint on, anything you get wrong when you check your answers, please mark or star those questions so that you remember to look at those again before the quiz. But I thought that would take a little bit longer here, but you guys still have like 45 minutes. So I thought finishing up Worksheet 2 might end up being homework, but I really feel like you guys should probably get that done in class. Except for question A. Question A we will talk about next class, and then I will ask you to come back and finish it before I have you turn it in. Of course, after you guys finish and check your answers, if there's something you want some quick clarification on, you're welcome to come up and ask.